I would also.
Oh, you got some?
Sorry, which one? Where's the fun?
But then again, like,
Oh, I can't.
can't order it.
You know, guess I can.
Wait, today?
Call it.
Wait, you're going today? You're.
And honestly, man, like, I eat.
I feel you.
Same thing with food. Or-
Here.
uh,
Awesome.
something, yeah. Oh,
It's time, don't get me or something.
I don't know, that's quite simple. I caught myself.
I mean, we could do it next week, but we should ask them.
Pretty sad, it's lost fluids, probably won't teach it again in another 2 years.
And it actually is.
That's what I put on my survey, I said it should be offered every year.
It is a fun, well, but even if it were an elective that was on the books, I think it would be taught every other year. That's how we tend to do it with the overridden electives.
Yeah.
This is a fun one. I think next time I teach it, I'm gonna teach it slightly different.
Also,
Well, every time that I teach a class, I realize something that I could have done differently. And I think in this particular class, I think you need to do a lot more examples.
Yeah, pain clubs.
Either in class or just like weekly, like practice problems with a partner. You know, someone to keep you
Yeah.
accountable, something that maybe is low stakes that you can turn in even if you're not quite sure what it looks like. And so I think at the end of every class, I give you an example problem that you have to give in at the beginning of the next class. And that could supplement the homework, because the homework, I think a lot of folks kind of just like they put it off and they're not doing it and they're kind of like listening in class and going like this, right? And then they just say the wrong thing every time I point to something. And I'm like, you sound like you feel confident, but I don't know if you should feel as confident as you are, or if you're on the spot. Because for me, when I was a student, my ability to like think in the moment would get compromised, right? And it's only when you're like really confident in what you're saying that you can say the right thing.
Yeah.
Right, so especially when you're learning something for the first time, and someone asks you, like, shit, I did know that, but I just said the fucking opposite, right? So it's hard for me to assess, but if I give you a low stakes weekly, or no, double, 2 times a week problem that you have to do in the time in between classes, maybe that works better. So 2 over the weekend, 1 in between the 2 classes.
I think this would be memorized faster too.
Yeah, well, this one, I'm putting up, so I'm gonna start class now. This class is already started. You have signed up for your final check-in? Or you sent me something? I know that we just talked, and I'm gonna verify that that's my calendar. Go ahead and book something like an hour.
Okay.
It may not take an hour, it may take 30 minutes. I may look at all your work and be like, yeah, you got it. You may nail it, you may not. The questions I will ask, right? So I'll ask a lot of questions about your homework, and in particular, I'll ask you about the choices you made. Because if you don't understand the work you did, because you did it with a friend, or because ChatGPT did the thinking for you, and you never sat and thought about what you thought, then that won't bode well, right? Because the whole point of the class is to communicate what you understand. So we'll start with something like this. And we'll talk about your mastery thereof. So if you want to think about that ahead of time, you want to think about what I might ask. And then I'm going to show you a shit ton of terms. And you're going to tell me all of them that you know. I really wanted to give you guys the, what's that thing called? The concept inventory test. But I don't know, remember that thing we did at the beginning of the semester? I want to give that to you just to see whether or not this class helped with any of those concepts. But I didn't want to spend class time doing it. So
So final check.
So, well, what I was thinking is that if you want, I can just send it to you and, or like, hand you a copy of it. And you kind of just do it on your own time. I just would prefer you don't look anything up to do it. Because for me, it's really just a map. Did I attempt to, some things that I was targeting? Did I actually impart those pieces of knowledge or not?
What did you say you amended on the slide?
For,
The check.
yes. Okay, what's the first equation called?
Conservation of man.
Good. Is there another term for it?
Continuity.
Very good. What's the second equation called?
Conservation of momentum.
Good. What else is it called?
Now you're supposed.
Good. Is there anything that can be derived from this that is quite common?
Yes.
Good, awesome. And what is that equation called?
The energy one?
PVV or PVV.
I think you're looking down here. I'm just saying this one here. What does this give you?
Press each other. I don't like to.
Good. I think you're looking at the terms. I'm just talking about the conservation of momentum equation. What does that give you?
About the short version of conservation?
Oh, for newbies.
Bernoulli's equation. So Bernoulli's equation comes from the conservation of momentum, not from the conservation of energy, despite how similar they look, right? Because what we do with the conservation of momentum equation is we make several approximations, including but not limited to whether or not density is constant, whether or not there's vorticity, whether or not there's inviscid behavior in the fluid. And then based on those properties, Bernoulli's equation gives you something that is constant either along streamlines and vortex lines or constant everywhere, right? Depending on what approximations you choose. What's this one?
That one would be the conservation of energy.
This one?
That's.
Where do you look at your notes? Don't look at your notes. Look at the screen.
When I
What's
meant
this one?
Something to do with like the. Oh, I know some of the terms, but I don't know.
I know some of the terms.
Oh.
it's like,
Conservation of momentum, but there's two.
like the same thing, but
Frames.
there's twisting.
Good, okay, I like some of those words, right? Conservation of momentum, but there's twisting now. I would just change the vibe is right? You got the vibe. Twisting, but not really twisting, more of,
With angle
Rotation.
yeah, there's rotation of what?
frame.
The frame. The frame is twisting. Right, so it's not just that there's vorticity, it's that the whole frame is moving. Potentially rotating, potentially accelerating, potentially changing its rotation, right? So those are all the terms that are included here, right? This is the speed of the frame, this is the rotation of the particle in the new frame that's rotating. This is the rate of change of the rotation of the frame. This is the frame's centrifugal force. This is going to be flung off inertial flame. Okay, what's this one? Good. What's this one? Where?
I'm pretty sure I've seen that when we talk about dispersion relationships.
Yeah. So I think you are identifying the omega. And of course, the difficult thing, and every time you teach physics, is that I have a limited number of letters. And so omega shows up when we're talking about waves, but it also shows up when we think about vorticity. So if I tell you that this is vorticity, how would you write omega?
Cross.
What's the definition of vorticity?
Cross product, right?
Good of?
BU. Something, I know what you're using there.
Okay, well, good. What does it mean?
How much velocity is changing a certain direction?
Is that what vorticity means?
No.
No, what is vorticity?
I like how it curls.
Right. Curl, that's an interesting choice of word. Isn't that also a thing?
So it would be like V times the force, the curl. I lost it now.
No, you almost had it. What is a curl?
It's
Girl.
Okay,
it's a space. I
so
wanna-
you're all doing the right hand.
Yeah,
It's a
I
change.
love the hand.
Change in acceleration.
No. Curl has nothing to do with physics.
so it's more mathematical.
It's a thing.
Well, I'm thinking it's kind of like the change of reference. Like what we mentioned over there. It's a cross one.
Not just a cross product. This is called. The curl.
Oh,
This is called.
oh, yeah. I mean, okay, you got it, but
You're almost there. There is definitely a dot product. It's not, you're not wrong. You're just like 10% off. Okay, so what is it?
See the gradient divergence function.
You tell me.
I always mix them up, cause I know like one is the,
divergence is right.
Why? So if we add both of your guys' contributions right now, we can actually use a mnemonic. And this is how I remember it. The divergence uses the dot product.
I'll never forget that.
Cross product.
Curl is pro.
Right? The curl is a cross product, the divergence is the dot product, and finally,
Wait,
what?
the gradient,
The gradient.
or del, whatever.
I don't have a cool mnemonic for that, but I can't figure it out at that point. Okay. These things are things. What does the first one represent? Not in terms of physics, in terms of math.
It's like how an array is moved into like another position over time.
Okay. I like, especially the hand motion. I think you have the right sort of concept. I'm not sure I would use those words exactly. Because array already is kind of thinking like maybe a tensor or maybe like a vector. And we don't even have to think about that. This could be a function.
Right.
Because what this is really telling us, the curl is telling us, is how it's rotating. The way in which that object is changing opposite to the direction it's going. Right? Because this is the change with respect to space. And the direction of the change, right? Because the cross product is always going to be tangent. So the gradient goes in this direction. And whatever the property is this way. So let's say the flow is doing this. Right? Flow is doing this. Okay. As you follow the flow, the way in which the flow is moving. Right, that's the curl. So the flow is turning around like this. The way in which the flow is moving, the gradient, the curl is out towards you. Or vice versa, if it's crossing this way, out towards you. Right? What's this one?
Parallel,
Excuse me?
right, if one uses sine, or opposite. You said that's tangent, so I'm thinking, one of them, I remember, uses opposite tree.
Okay. Let's draw. I'm a good drawer. Everyone knows that. They're like, wow, that's funny. You so draw. Okay, so this one. How this spinning good. Right? This one, divergence. Interestingly enough, if you listen to the word, it diverges. Right? So this divergence is measuring basically how is it changing in the direction of where it's going. Right? So if you think about you're sitting on the top of a hill, okay, and you're looking down, this is gonna be a bad analogy. I don't know why I started with this. Okay, I'm doing it anyway. You're standing at the top of a hill and you're looking down, and it's sort of rocky croppings in all directions. And maybe on one side it's a side you hiked up on and it's nice and a low slope, and on the other is a cliff hang, right? The divergence is talking about how the function is changing in each of the directions that the function is going. So as you walk in each of the directions, if I walk this way or I walk this way, how am I falling down in those directions? Right? As opposed to this one, which is talking more about how is the object rotating. And it's not just rotation, how is it changing tangent to the direction of the function itself. Right? What happens if I do both of these? What?
I feel like this is Ian, we're getting yelled at about Ian.
You're getting yelled at, Indiana? I would never yell at you. This is my favorite identity of all identities. This is B312. And we take advantage of this identity all of the time in order to make our lives easier as physicists. Okay. This is always because this is the change in the direction, and this is the change tangent to the direction, right? So therefore, they could never be aligned. You can put them back in the other direction. Right? If you flip these are commutative operators, so you could do the del cross on the inside, and that might be easier to see. And this is in your book, Appendix B312. There's a lot of things about fluids that I want you to understand in this class. A lot of things that I hope you walk away with and you're like, wow, I understand water good, or the atmosphere, or something like that, right? Some stuff that is really fun. But the fundamental stuff that I think is helpful for your career as a physicist or as someone who works in mathematical sciences is to understand the relationship between the mathematics that you see in fluids and what their physical interpretation is. Because it turns out a lot of the mathematics that you see here is empirical. Unlike when you think about how a charge is moving, right? You don't have firsthand experience for how a charge moves around a magnetic field. You just have never seen it before, right? But you've seen water. And so this provides us with a unique opportunity to draw physical examples to mathematical operators that might otherwise seem obscure and opaque. And if we can understand them well in the concept of fluids, then we can use these same concepts in electromagnetism and in general relativity and help us to understand stuff that certainly does not make as much sense. So for example, when we talk about the divergence of E, right? Let's say this is an E field. Well, of course, that kind of makes sense because there would be a charge here. And if there is no charge there, then there's certainly no divergence there. So typically what we do is we say something along the lines of del dot E, the divergence of the electric field is due only to charge. The charge where? Something like that, charge enclosed, some region. So if there's charge in the region, then you have divergence. There's no charge in the region, you don't. Okay. And what does it mean when I write this? Why is it 0? There are no magnetic charges. This is a fundamentally important thing, right? Because you can never have a single plus or negative, there's no N or S magnetic charge. And because of that, then there's no divergence from a point source. There's curl, right? We all love our bar magnets and playing with them as kids, right? But think about how different the world would be if this wasn't the case, right? There's very little that, as far as the physics that you know about and you know and love, there's very little that precludes us from having a positive, or sorry, having a magnetic charge, right? It just seems like an object to you. Right? So it's just a weird quirk of the universe that there isn't a magnetic charge, right? It's not a weird quirk of it. You'll learn. Okay. These make sense? You're gonna feel confident doing them for the rest of your life?
Use them, heat them,
Yeah, you can use them in E&M. Maybe you'll come to my vector calc class next semester. What's the next one? What's this one? What's the reason that I went on this tirade? What? It better be. Goddamn better well be, you know what I'm saying? Okay, so what does that mean?
Is how fast the thermal velocity space is twisting early.
Yeah. Again, 95%. I heard both of you. How fast? I would just change the word because it doesn't always have to be fast. Sometimes it can be direction, right? That's the only modification I would make there, right? But that's exactly right. It's how is the velocity changing with respect to like twisting, right? That's like the good vibey way to think about it. And because changing direction, just like we think of acceleration, doesn't have to slow or speed up the part, so to speak, right? Good. So the vorticity is really talking about the motion of the flow, maybe around something like the vortex. Good. We feel like we can understand all these. Say if I hand you a sheet and I ask you to define them all, you'll be like, Chingy? And what's this one? Let's see, since they did all the rest of them, you want to tell me just what equation this is, not necessarily what the terms mean?
I'm actually not sure.
Okay,
It has to do with the Bernoulli's equation.
this one is the Bernoulli's. This one is where we get the Bernoulli's equation from. This is a simplification of a different equation. In fact, this one derives from this one, but I did some trickery to it.
Assumed a lot of stuff.
What?
So you assumed a lot of stuff.
No, actually, I did even cooler trickery. I took advantage of this relationship. If I take advantage of this relationship, this is the gradient of P, right? And I can always write G, which is the gravitational potential, as the gradient of something that's the potential, right? The phi, for example. So the force is the gradient of the potential. We know that. So these are both gradients. So if I take the cross product of this whole thing, then these two terms automatically disappear. You remember that witchcraft? And this thing becomes rho d. I take the cross product of this. What? Omega. Rho d omega. And then over here, you know, you kind of have to work out what happens in this location, and there's a little bit of what we call math. But it gives you this.
That's just telling us how vorticity can change.
Yeah.
How much it can change.
It's a vorticity like conservation essentially. So this on the bottom left hand side is the total derivative of the vorticity. And the only ways to generate vorticity are through this thing and this thing. Okay. This one or this one?
That one.
This one, yes, exactly right. Yeah, right. So you see this del squared operator, and if you think in your heart's heart del squared of something, you know, with the rate of change with respect to time. So let's say I just drop that. Right? D omega dt is equal to del squared omega. That's always going to be diffusion of that object. If on the left hand side I had a spatial derivative, then we wouldn't necessarily characterize that as diffusion. Oops.
We're recording today, right?
I'm not posting it.
Why?
Hi.
Say correct.
Whoa. Okay. Reported. Well, I hated it. Okay. Yeah. No, I can post them all. I just haven't been doing it. Does this make sense? So as I mentioned at the beginning, you will be expected to know all these. You should be contacting me for your final check-in. And then your ability to tell me how good you know things is your grade. Okay. I also expect you to know some of these words. Fuck, that's a lot of words. Okay, it's not that many words. I think you know a few of them. Anyone want to give me just one? So we'll just go, let's see how many points we can collect. Raise your hand, then you'll just shout them out. Wait, I can not call them the same person. Yeah, go ahead.
I'm most confused with Reynolds number because the way I think about it is just kind of like the ratio aspects between like fluids of different sizes. Because like when we talked about it, it's just if something's 10 feet and you want to make like a foot long.
Yeah. Okay, so I get your misunderstanding there because I tend to talk about it in the context of similarity solutions. And so therefore I talked about the advantage of using the Reynolds number so that we can convert between different fluids. But what does it really mean? Well, what it really means is it is a ratio of the strength of the advective term, which is really thinking about the inertial term, the inertial acceleration of the flow, compared to the viscous terms or the viscous stresses in the flow. So this is really a ratio of something like the advective term, which if we go back, okay, the advective term looks like this, the row outside, that's the strength of the advective term, right? Compared to any viscous term that might exist. And all the viscous terms, they have the same type of strength. You'll notice that they're all mu based. right? They carry a mu with them, and they have a u, one version of u, and on the bottom they have two lengths. So they're all of the same scale, right? So the Reynolds term is simply the ratio of the inertial term to the effective term. And what we saw when we were discussing laminar flow or turbulent flow is that while we expect, like physicists, like every good physicist knows, that a ratio of 1 means that they're equal, that's not how we in practice talk about them in fluids because of the relative size of these physical terms. And what that means is that this only really starts to become a turbulent flow for most geometries when the Reynolds number is something like 10 to the 6, right? Now notice there's no units associated with that. This is a dimensionless number. So really what this is saying is the only time you really start to get into very turbulent flows or transition towards turbulence is somewhere between 1,000 to 1,000,000 times, 10,000 to 1,000,000 times their relative strength. Okay. If we think about what the implication of that is, right? It's that the viscosity here, if it were like, let's imagine a different world in which the actual strength of these terms were equal. Nothing would happen, right? Because any ability for you to try to advect motion would immediately be sapped away. Thinking about what the viscous stress terms do is they divert velocity or they divert whatever you're trying to do away from the direction of motion. As I move my hand across the flow, right, it drags velocity down into the flow. And if it were just as good at doing its job as the pushing term, then nothing in the flow would happen, right? So this term automatically starts off with a huge disadvantage. You need water? Good. Want to pause? Okay. Don't die, please. Don't kill us, please. Okay. Does that kind of make sense what I was trying to say there? Does that break it down a little bit? You seem less happy. You still happy? Okay. Okay. Does that count as Daniel's word, or do you want to choose a different one?
I mean, you got that.
Oh, okay. All right. He's calling it. That's his term.
No heat.
No heat. Very good. Yeah.
That one means that there's a certain amount of molecules needed to present a fluid, and the way you know how many you need is if it can communicate collisions.
Good. Yeah. Yeah. The only thing that, I mean, this is a great definition. I would just add the caveat is when we think about the number of particles, we also want to talk about over a certain region of space. Right? Because, you know, you can always scale up and say, well, all of a sudden. So for a great example of this is the very top of the atmosphere. The atmosphere that we're in right now is certainly a fluid and participates in the continuum hypothesis. As I move up, let's say in a weather balloon, I eventually hit as high as the weather balloon can take me. And now I need some other mode of transport to the top of the atmosphere. And as I move towards the top of the atmosphere, I still have quite a number of particles. There's tons of particles up there. But the time between collisions, as you mentioned, is quite small because there's real big distances now, right? And even worse than that, there are some particles that once they gain enough energy, right? So there's probably more energy per particle, maybe in some cases down at the surface. But a particle that is moving very quickly, it's going to bump into another particle and it's going to lose that high energy quite quickly. But if you have a high energy particle at the top of the atmosphere, it'll just leave. Right? There's nothing that it'll bump into. And so we can't use the continuum hypothesis out there. You can use statistical mechanics, you can use Maxwellian distribution, but you can't use the continuum hypothesis. Okay. Who's next? Kevin Metzlin?
The compressible like like. Like how the density changes when force is applied to it.
Mm-hmm. The density change of force, but yeah, okay. What's an example?
Like air.
Air excuse, I don't know. Famous, okay. So that's like what we use for factors. And buildings. Good. That's what you were saying, Lynn?
Yeah, convection, just like the trans.
Transfer heat in a fluid, good. Is convection a heating or a cooling process? It's a cooling process, yeah. Right, because it's a way to get rid of heat. And you're trying to restore stability to the situation, right? Because if you have a heat source that's underneath a cold region, that's necessarily unstable, right? And so convection is the reorientation of the fluid to try to put the hot on top of the cold.
Convection of those.
Yeah, so you put the heat's on the top though, right?
Yeah,
Or oven, yeah. Was it on the bottom? I don't know. Could be on the bottom. Good question. I don't even fucking know. I guess no, there's a broiler on the top, and you're right, there's a heater on the bottom. But in both cases, what you're trying to do is trying to get air to go. What's the difference between an oven and an air fryer?
Air fryer is a convection. Right, so.
So just size.
Yeah.
Yeah. Size and easy to use. So because it's so much smaller and the area that it needs to heat up the air is so much smaller, it does it quickly. Whereas your oven is quite large and it has a large thermal inertia. And so if you want to just fry up your tater tots and your chicken nuggets really quick, you throw them in the air fryer, not in the. And also air fryer is really smart, right? Because what they decided to do is instead of having like a pan, they put this like grid so that you can have it airflow underneath. And they're like, help it's fried. So that was okay. Good. That takes us to the top. Let's keep going. Oh, we're doing this all day. You have anything else to do? I mean, we can talk about planes, but I think that you probably. So this is I was thinking about what we wanted to do today, and I was like, do I want to give them a lecture on something that they're immediately going to forget? Probably not.
Fair enough.
So we can talk about planes. We can talk about shocks. To talk about shocks, you really need to understand a lot of the like adiabatic jumps or whether or not there's heating. So you really want a little bit more thermodynamics, because that's one of the ways that we connect it energetically across the shock. We can talk about planes. We can talk about lift, but we might just do that for 5 minutes right at the end. I mean, it's straightforward, right? You've basically seen it all now.
Oh, I was gonna say body forces, forces acting.
Good. Yeah, they act on the entire parcel, for example. So you got some good ones. What?
No slip condition? Yeah. What is that?
What is that? What does it mean, no slip condition?
That there's friction on?
You've heard this.
Guessing.
You heard this condition in 2500.
No slip. So there's nothing.
Is that kind of like the boundary condition? Like when it reaches like goes to zero at the walls?
No slip condition just means that you're not allowed to have the fluid slip by anything else. So the first time you see this boundary condition in the text, it's called the no slip condition. You also see this in this one. So what you can do is you can figure out how many times it rotated, right? But if I do it like this, that's really not staying on there good. You do it like that, right? It rotates while it moves. And so you can directly correlate the rotation to the the distance that it travels, right? But if I push it and then it rolls, then it slips before rolling. You see? Just look
Is that like the same of a bowling ball?
Yeah, bowling ball slides and then rolls. Slipping friction, sliding friction, and static friction, of course, are different frictions. And that's just necessary because if you recall, there's intermolecular forces between these two objects that give them friction in the first place. And in order to overcome them, it takes more energy to first break those connections than to keep it in motion. Sliding friction is usually smaller than static friction.
Coriolis.
But you just won. You gotta
There's
win.
a lot.
No, but you can't get all the points.
The conservation equation is the conservation of mass.
Got it.
The viscosity remains constant.
Viscosity remains constant, and what else? It's the second condition there, it's a little trickier. Okay, it's that the stresses are linearly related to the forces. And all we mean by that is there is something like, when you write S, or if you write tau, which are both the stress and the, stress tensors and the viscous tensors, tau and S, they relate to the first derivative, d dx of u, right? That doesn't have to be the case. In fact, that is clearly and totally empirical. So we have found in nature fluids that don't do that. Those are non-Newtonian fluids. And sometimes they are called shear thinning, and sometimes they're called shear thickening. The shear thickening means that when you put a force on it, it actually behaves more like a solid. So they're non-linear in the way that they respond to forces, shear forces, right? Shear thinning means once you give it a smack, it actually starts moving faster. So an example of that, a shear thinning, would be ketchup. If you want ketchup to come out of your bottle, you hit the back of it. And you think to yourself, well, I hit the back of it because it's going to start moving. It's not. The reason that that works so effectively for ketchup is because it's shear thinning and it gets the particles moving because it reduces the internal viscosity when you apply a force. Smart brain. Fluid dynamics class. I learned how to use ketchup. What's an example of a shear thickening fluid? Oobleck, right? That's the stuff that you can stand on and you'll sink, but if you run in it, it'll be like ground. We could make some for our final.
Why do you be done because I've never seen it?
What?
Isn't that what quicksand does too?
I have never been in with.
Yeah, me either. That's what I'm saying. I don't know if it's a
Based on all the books I read growing up, I thought it'd be much more of an issue. Turns out you don't encounter it. But quicksand, I believe, is a liquid. Go down.
I forget if it's isentropic or isotropic. But I'm gonna say isotropic's the one that always stays the same, like the volume, like the space. Or is it isotropic?
Interesting. ISO definitely means something. What does the word ISO mean?
Right.
Same. Good. So isotropic means isotropic means same everywhere. Isentropic means same entropy everywhere.
Like same E.
Isovolumetric means same volume. Isobaric means good. Now you got them all. Isothermal. Let's go. Let's go. Right, you just have to know a little bit of the construction of the words and you seem like a genius. Hey, what else?
Dude, barotropic. Now. That was the same density.
Same. Barotropic is the same density?
Well, the density, no, the volume depends on the density only.
The density depends on the pressure. The density depends on the pressure depends on the density. So in an ideal gas, is that a barotropic equation of state?
No,
No, why?
it's EV equals nRT, so temperature is. That volume and pressure changes with the temperature.
Right, so the way that I would write this, right, if I needed to write it down, is that for an ideal gas, pressure depends on just
Number of moles.
right? Right. That's the difference. Okay, what's advection?
How temperature rises.
That's convection. Vection, though, you know, correct motion. Vection, I think, comes from vector. The move. What? Yeah, so this one is actually agnostic as to what you're bringing. It's just the transfer of. The advect would be the bringing to. Add meaning to, vect meaning bringing. Convection is bringing within. Right? Confluence is to bring something within. And congruent is matching within itself. Okay, barotropic, you got that? Body force, so you got that? What's this thing? No, you said body force. What's this one?
That's where the surface tension changes, or that's where.
I think you're thinking of free surface.
Okay.
The free surface would be like, you know, a layer between two fluids or the layer at the top of a fluid. You're right, at the free surface, what happens there is that you have surface tension forces holding things together. But that's not what this one means. What?
I just don't think this matters right there.
Viscous, yeah, viscous matters in the boundary layer. Do you have a boundary layer if you have no viscosity? What? No. Boundary layers disappear without viscosity. What?
It's just at the surface.
It's not just at the surface. In fact, it's rarely at the surface.
If you have no viscosity.
If you have viscosity, sorry, let me rephrase that because I might have just confused you. Or maybe misunderstood you. You said if you have viscosity, right? The location of the boundary layer is not at the top where it interacts with another fluid or interacts with air or something.
It's where it's 0.
It's where it's 0. It's where the no slip condition exists, right? And necessarily because of the viscosity, you have a region which is different than the rest of the flow, right? So let's say you're doing a computer simulation of flow inside a 2D square, right? And generally speaking, in the whole circle in the middle, fluid dynamics is going just perfectly well. And it's just towards the edge that there is a little bit of the fluid interacting with the wall. And the wall says, hey, bud, you got to go to 0 here. So that enforces a change in the flow, right? The flow wants to just slide past and not even care that the wall is there. But if you have viscosity, then it's required to go to 0 at that wall, right? This is why we have the driven cavity problem. As we move that top plate to the right, you can create vorticity in the box itself because it sets up a boundary layer that drags the flow. And as it drags that flow, it starts to generate vorticity. Other examples of boundary layers in your day-to-day life?
Right?
Driving? Driving's actually a great one. Where do you see boundary layers when you're driving? What? Well, are you sticking your hand out of the window? This is a baseball. That's cool, right? This is smoke. So the baseball's not moving. Unless that wasn't clear. It's rotating. Baseball's rotating, but it's not moving to the left or right. The air is moving past it. And they can simulate this with the Reynolds number appropriately. Okay, where is the boundary layer? How far out does it go? Is the boundary layer out here? Boundary layer out here? It's almost touching, right? And in this particular circumstance, look at how cool this is. This is stagnation of a streamline directly into the surface, right? And here it does bend over. And then this is where you have turbulent boundary layer. We talked about that on Monday's class. It's not laminar in this boundary layer. So this should already be able to tell you what the Reynolds number of this ball is. Do you remember? Didn't memorize the Reynolds number. Of course. Thank you. Straight to the point. Correct, but not right.
It's like a billion times the 6 or something.
10 to 6 would be a million. This is slightly less than. This is something like 10 to the 4. 5, 10 to the 4, 5, 10 to the 5. Just slightly different. Yeah. Good. And you can see there's turbulent winking as well. Anyway, that's the width of the boundary layer, very small. When you're driving, you stick your hand through the boundary layer to get out to the flow. You're never like in the safe boundary layer. That's why it's right here. It feels like it's rushing by you. Because remember that the air on the surface of the car is with respect to the car. Oops, I guess I can do it here too. No, I can't do it here. Okay, I just wanted to show you that one cool picture. Okay, what's this thing? Never heard of that in my whole life.
Which
Which one?
Look at that. Yes, this is the front by solid frequency. So if you don't have convection, if the flow is stably stratified vertically, and you perturb it, based on how the temperature or the pressure changes as a function of height, this is the maximum amount of waves that you can generate. Right? The front by solid frequency tells you whether or not you have gravity waves or if you're convectively unstable. So this was having to do with the dispersion relation, omega equals something k, and then the inside could become negative, and if the inside became negative, then instead of having waves that go up and down, you have convection. Right? Nice. And it's fun to say. It's like kind of cool. There's like even little umlauts and Grundpfeilsale. I don't get to say fun things in class. What's the point? Okay, what's next? What? It looks like calorie, right? Uh-huh. Or what's a calorie? It's an energy thing, right?
It's a measure of like the internal energy of something.
Close. So we were talking about this a little bit, maybe it's too long ago. We were talking about this in the context of, we had the energy equation. And we said that we needed a way to relate some of the properties of the flow, like the density and the temperature and the pressure. Those are not inherently energies, right? So what does the caloric equation do? Well, usually we call them caloric equations of state, and it's the way in which we match these things based on some energy relationship. Right? So this ideal gas law could be used as your caloric equation of state as long as you say something along the lines of like, yeah, it's adiabatic. So if you use adiabatic plus the ideal gas law, you can create something that has like PV equal, or PV to the gamma equals a constant, right? And that would be your equation of state for that. Cash? We did this one? Did we do this one? You did this one? This one we did? This one we did? What's this thing? Control. Control what?
P over S.
V over S.
That's
It's a slash.
surface.
Volume surface, good. So what's a control volume or control surface? When have I used that concept?
It's like fixed, it's fixed,
What's that?
like the space is not changing.
Yeah, you could imagine some box. What's special about using a control volume? What am I trying to do? Say you have a wind over a house. How do I use the control volume to solve the problem?
The house's volume is not affected by the wind. It's staying the same.
Yes. Let's say I have the wind over a house. I have a control volume behind the house, and you're trying to find the pressure on the back wall of the house. This is a home problem, right? But asks you to use a control volume. You know, that ostensibly. So what does a control volume do? It's a tool. Helps us to understand how inputs must equal outputs. Right? That's all we do. We take the Navier-Stokes equation, and we say, I'm an accounting firm now. If I have flow come in, then I either have to account for it going out, or it has to result in one of these other types of forms. So flow going in can increase the pressure, but it has to do so with these two parameters, right? We like this one, oven. Nice discussion about that. What's this thing?
Force.
What?
The force that's due to earth rotation.
Due to Earth's rotation. Good. Does it have to always be Earth's rotation?
Spinning frame.
Any spinning frame will produce this. Yeah. So the guy Coriolis is just talking about a frame in general. So if, for example, you're throwing a ball on a merry-go-round, that's still the Coriolis force. Is it a real force?
I think technically.
Fight.
When people say it's not real, okay. Or it's not real. Well, because it's the result of that.
Yeah, right, so we tend to call it a fictitious force only because it doesn't appear to an outside observer. So an observer in an inertial frame does not see that force. Right, they see the ball go straight. They're like, why did you throw it at, Bob, who was gonna be there in 2 seconds, right? Good, what's this thing?
How something spreads apart.
Good, in what way? How is that different than this?
Oh. Because it goes from high to low, or low to high.
Good, right, yeah, so it's attempting to equalize, right? Advection really doesn't care. Advection is going with the flow, it's just like a chiller. Diffusion is attempting to fix concentration issues. So if there is more of something in a certain location, the diffusion will occur until everything is. What's this one? Good, so what do we mean by that? Why would we use a dimensionless number? Give me an example, what does it do? What's your favorite one? Don't say Reynolds number. What?
Where we use that?
Yeah, well, which number is we want? Because obviously you could say like 4. Yes, not a dimensions number. What?
0.
Numbers themselves, you're right, are dimensions. That's not what I mean by the word dimensions.
Yeah.
It's a technique we use in physics in order to achieve something.
Trying to see relationships between things.
We're trying to see relationships between things, and so therefore,
We use a dimensionless number so that we can see. Just like how it relates to others.
right. So we take quantities like the velocity, divide by some scale velocity. We take quantities like the length, and we divide by some scale length. We take quantities like the density, and we divide by the mean density. And when we've done this, we can divide all of those out of a term, say, like this term here. Okay, we're gonna take this and we're gonna divide this by the mean density. Mean density to the bottom, and some time scale, tau goes on the top. And now tau divided by the mean density acts like a reference point. Because the same thing will happen here, right? And you can say, well, how do these things compare? This term to this term. And then you can decide whether or not one thing is more important than the other. This is a very important mathematical tool when it comes to interpretation, right? Because if you have something complicated as fuck with this, right? And your job is to actually do work on a day-to-day basis, how do you know to throw this out?
It's dimensionless number is so small.
Right, yeah, this d omega dt, think about how big the omega is, say like some reference omega, over some reference time, maybe a few seconds of your simulation, you'll see that this simulated value is quite small and therefore you can throw it out, right? As opposed to perhaps you have this, and this object that you're simulating is right on the equator, and you say, well, no, we really can't throw that out because the effective gravity is quite different, right? But if you're simulating 2 different things at the equator, right, and you're making a comparison between them, then you might say, well, the difference in this parameter is close to nothing. So let's not model it. It'll be the same for both. Throw it out. See? Okay. What's your favorite dimensionless number? Give me one.
They also.
E is a constant. It is true that it has no dimensions, but it is not a dimensionless number in the context of what I'm saying here.
I was trying to use length, but it was like arbitrary, I don't think it was like.
No one loves planes here, huh?
So like friction. We're told to ignore it sometimes.
David, do you remember the name of any dimensionless number? You said one earlier. Sorry.
Oh, density.
Let's start with an M. It is the Mach number. Okay, M is the Mach number and represents U divided by C. It's the advection in the flow compared to the ability to propagate information in the flow. Mach less than 1 is subsonic. Mach equal to 1 is sonic. Mach greater than 2 is transonic. Or no, sorry, supersonic. Transonic is above 0.3, I believe, 0.3 to 1. So most of the fluid flow equations that we think about, we have this ability to build, right? So a boundary layer that offsets the flow in the direction of motion. And you cannot build that if you're moving faster than the sound speed fluid itself, right? So you need different physics. Anything else? Mach.
The Reynolds one.
The Reynolds one, right? What's the Reynolds one?
Like a, oh,
We usually write it in RE. This one we write as M.
the,
What? U over like that.
yeah,
It's okay. You don't have to have them memorized. Just my favorite things. Is there, can we put in the back? Oh, there's some fun like visual resources. Chapter 9. One other fun ones are like the Prandtl number, the Rossby number. I just want to see what they all are. They're not listed as like a list. If you go to chapter 411, that's probably the closest that you'll get. Some fun ones, just so you can know these numbers. The Skluchal number, which is the ratio of the unsteady to the advective term. Skluchal. Strouhal. There is the Reynolds number, you just saw that, the inertial to the viscous force. The Froude number. Froude number is the inertial to the gravity term. Okay, the Froude number is actually really helpful when you're thinking about, say, the advection compared to gravity. Right, so this might be more important for things like is gravity an important part of your restoring force? There is the Mach number, we saw that one already. There's some other fun ones in here. The Eckhart number is an energy number, so that's the kinetic energy divided by the thermal energy. The Prandtl number Prandtl number is Prandtl. That's the momentum diffusion compared to the thermal diffusion. You have a couple like the Weber number, which is the inertial force compared to the surface tension force. You have the bond number. It's not 007. It is the gravity force to the surface tension force. You have the capillary number. You've heard that. And the capillary number compares the viscous stress to surface tension. Can surface tension overcome viscous forces? There's more. The Rossby number. These are like geostrophic numbers that you'll find in chapter 13.
They don't have names after people who just chose to do things to compare, huh?
Yeah, bro, that's the if you just were 200 years ago, you could have the name of something right after you. So for example, right, Coriolis, that's a pretty famous term. The Ekman number is the viscous force per unit mass divided by the Coriolis acceleration. The Rossby number is the nonlinear acceleration to the Coriolis acceleration. I think that's it. That's probably the only two that I know. Okay. Fun, right? Oh shit. I should not have gone on this. What's this thing? It's hard for me not to go on tangents.
Gravity, so like stuff.
Yeah. Can you expand on that a little bit? What do you mean by the ocean?
As I mean, like that causes waves, that's due to gravity.
Okay, so yeah, so that would be how we think about the tides. But what do gravity waves tell us? Where do we find gravity waves? Convection and gravity waves are related to the run by solid frequency. When you have an internally stratified media, that is layers of stuff on top of each other, you may have some disturbance. As it moves up, if the restoring force is gravity, gravity is trying to pull it back down again. The upward force is buoyancy, so there's a natural balance between the two. If the parcel of fluid is now lighter than its surroundings when it moves up, you have a convectively unstable region and it goes up. If it's now heavier than its surroundings by the time that it makes it all the way up, then it comes down, and the restoring force being gravity calls this thing a gravity wave. A wave created by the fact that gravity is the modulating influence. Okay, what's this thing?
Viscosity is 0.
No viscosity. So unlike irrotational or isentropic, ice being the ISO, same everywhere. In is what? 0, right? None. Yeah. So no viscosity. This in would be the different word for viscosity, but it's an adjective. So a viscid fluid would be one with viscosity, and an inviscid fluid would be one without viscosity. Similarly, what's this? No rotation. So why is this not irrotational? So why is this not IN rotational if this is inviscid?
What's the property of the thing itself? Let's do what's what.
That's even dumber.
Oh, it's even done.
That's just how English do. There's a secret law of English that if it's irrotational, irreplaceable, cannot be replaced. So it's not irreplaceable. which it should be if you use this letter, IN, right? But depending on whether or not it starts with an R, you just double up the R. Fun, right? Okay, let's go down to here. This one's important. Layers. And what's the derivation? How do we find the etymology? Where does this word come from? What? Yeah, laminate, right? So things are laminar. They arrive in layers, and importantly, they are parallel layers. They don't interact with each other. This one. Observation moment. Good. This one. We already talked about this one. We already talked about this one.
The way particles can move. It's like, isn't that trajectory line?
Yeah, so there's three different ones. There's a streak-like, a streamline, and a pathline.
That's like its actual pathway.
Pathline is
The different paths I could say here.
okay, why don't we look that one up? This one's gonna be important. I'll add the rest of them here. Because we're running out of time. Perfect gas, ideal gas, and potential density. You heard of that? This one we really didn't do that much in class. You would do this more if we did this in the context of like action layers or more geostrophic flow. And some of the stuff that we would have done, we did the conversion of the Navier-Stokes equation to planetary scale objects. The potential density is a representation of when we think about that stably stratified media, and I move my blob up where it should be, what is the density that it should be at that location compared to what it is?
I like the Jupiter problem. I think we did something like that.
Maybe. I'm forgetting what I assigned, so that's just my bad. But I found it connecting it. Reynolds number we did, what's this thing? What? Kind of, but in the context of the tensors that we talked about. What?
Frank is rotating, so.
Remember how we started off this class? We had some boxes, right? And we did stuff like this, right? As opposed to this. So that's all I'm trying to say. What is this? String. Certainly a string, right? When the angles get closer, that's a string. The angles remain intact, but they change relative to the origin. That's a rotation. That would be the major difference that I would make sort of in terminology. Shit about that. What's this one? So these ones are really tricky because they seem interchangeable. But really they talk, and this is the difficulty, of course, associated with an equal sign, that we have this concept that they are the same thing. But really, we sometimes think, so for example, about the continuity equation. Here, you have this thing, and I can put this on the other side such that the changes in density are only due to bringing density from somewhere else, right? But that doesn't mean that they are the same thing, right? If they're equal, it doesn't mean that they're the same. And so similarly, we can think about the word strain and the word stress as one being the thing and the other creating the result, right? So the stress tensor is a measure of all of the forces that are being impacted into the fluid. And then you create strain. That's sort of the easiest way to think about it. Now, that's an oversimplification, of course, but it's what I'm trying to get in the last minute. Okay, last one.
What it communicates.
I would just change it slightly, how well it communicates velocity. In a direction tangent to the velocity. Because usually with viscosity, or with having a viscous motion, I am pulling in this way, and yet I communicate velocity downward into the fluid. Or you wouldn't do that if it was viscid. Okay, well, I'm sorry that you didn't get to learn anything about planes today, but planes go in the sky. And they often don't want to fall out of the sky. So if you take a plane, has anyone here been on a plane before? Has everyone been on a plane before? I've had lots of people have it, so. Do planes want to fall out of the sky? No, because planes are really suspended in an air jelly. They have a lot of air below them and they have a lot of air above them. We just can't see it. Right? Let's always remember that just like fish cannot see the water that they are in, we cannot see the air that we are in. Fish can probably see air and we can probably see water. Cool. Questions, comments, concerns? Okay, I will see you for your final check-in. Contact me. Prepare for like an hour. It's everything we talked about today. It's your homework.